Hello everyone, this is Anil. In Basic Control System, this is the fourth lecture. So in the previous lecture, I had discussed about system classification. So in the last lecture, I have covered static and dynamic system, causal and non-causal system, time invariant and time varying systems. So one more system classification is remaining, that is linear versus non-linear. After this, we go for block diagram reduction techniques. So what is linear and non-linear system? So when we discuss about linear, the first thing comes to our mind is that there is a straight line relationship between input and output. So mathematically, it can be described as like this. So consider the slope 1 over k. So output y equal to 1 over k times u. So before we conclude, we take this kind of definition for linear system. Let us see how many practical systems going to satisfy such mathematical expression. So in mechanical, consider the spring. In spring system, the output is displacement. So displacement x equal to 1 over k. K is spring constant times input. What is input here? Force. So this satisfies this kind of relationship. Next, consider resistive element. So when we give supply voltage V, the current I is the output here. Current I that flows through the resistor. So output I equal to V over R. Okay. So this also satisfies this kind of relationship here. Now let us take one more example, capacitor. So when we supply voltage across this capacitor, the charge will be developed. So charge Q equal to C times V. So this is also in this form. But when we take simple this R and C in series combination, okay, in series combination, when we take these two elements, let us see the mathematical expression. Okay, so supply voltage V equal to I times R, and the voltage drop across this capacitor is Q by C. So that Q by C I have written here. So to express everything in one variable, I have differentiated here. So dV by dt, R di by dt, 1 by C, dq by dt is written as I. Okay. So see this relation, this is not in this form now. Okay. Not in this form now, this expression. Okay. So let me use the marker here. So final, this expression is not in this form. Okay. So before we conclude this kind of definition, let us further work with this definition. Okay, we have now y equal to 1 over k times u. Initially, we scale the input. Okay, alpha times u. Then see what is the output now. So the new output will be 1 by k times u bar. What is your u bar? Alpha times u. That has substituted here. To take the alpha outside constant. Okay, so 1 by k times u. This 1 by k times u is again y. Okay, so here alpha times y. So observe here. So when we scale the input, right, we have scaled the input here. So output is also getting scaled here, alpha times y. So whatever this alpha belongs to some real number. Okay, so this is known as homogeneity. Okay, homogeneity or scaling. In the similar way, consider here two different inputs. Okay, u1, u2. For u1, this is the output y1. For u2, this is the output y2. Now you take combined, okay, u1 plus u2. So what is the output here? 1 by k times the new input is u1 plus u2. So take 1 by k in bracket here. So 1 by k u1 plus 1 by k u2. 1 by k u1 is y1. 1 by k u2 is y2. So overall it will be y1 plus y2. So what I want to say here is that if you give sum of inputs, the output will be sum of outputs. Okay, this is known as additivity. Okay, additivity or superposition, this concept is known as. So we have defined here two things here, one is homogeneity and one more is superposition. Let us see now how many mathematical operator do satisfy this homogeneity and superposition. So initially I have considered here differential operator. To this differential operator I have scaled it, and since the alpha is constant, we have taken alpha, again have dx by dt. Then you take sum of inputs is equal to individual output d dt x1 d dt x2. here I taken linear combination of differentiator and integrator. Okay, this also satisfies the linearity these two properties, homogeneity and superposition. So now so we have defined here linear operator. Okay, so we defined a linear operator L such that it satisfies these two properties, homogeneity and superposition. Okay, so this linear operator on alpha times x, so alpha will come out linear operator on x. Okay, this is known as homogeneity. Linear operator, two different inputs, x1 and x2. So linear operator on x1, linear operator on x2. We through combine we have taken like this, alpha times x1, beta times x2. So since alpha and beta are constant, belongs to real number, so we can take it outside. So alpha times linear operator on x1, beta times linear operator on x2. So we say an operator L as linear operator if at all it satisfies homogeneity and superposition. Now come to the definition of linear system. Okay, we define a system as linear system when this kind of relationship holds. Linear operator on input equal to linear operator on output. So let me use the marker here. So linear operator on input equal to linear operator on y. So come back again to this example. Okay, see here d dt, it is a linear. Okay, so linear operator on input. Okay, we already defined here d dt is a linear operator, and here 1 by c is some scaling factor k, so linear. Okay, r scaling factor, again we have d dt, it is also linear, so linear operator L2 on y, it is in this form. So the mathematical representation, finally it has to satisfy this kind of representation, then we can say the system. Okay, the system is a linear. Okay, so this is the last classification of system, linear versus non-linear. Now we go for block diagram reduction. See, in control system, basically what we have one controller, we have an actuator, we have one plant. Okay, and in feedback, suppose we take on feedback here, output y. Okay, in feedback we have like sensor here, some summing point. So this is how we represent it, right? In basic control system. Okay, we have some input here, reference r, output y. Okay, some error signal here, some input signal u here, some v here. So there are many blocks involved in feedback control system. Classical feedback control system, there are many blocks are involved. Now we want to represent this together as single block. Okay, some controller, actuator, plant. There are three blocks, right? So we want to represent it as a single block. Okay, to represent a single block, we need to understand some basic connections. Then we go for manipulations. So the first one is series connection. If two blocks G1 and G2 are in series connection, okay, or cascade connection, see the mathematical derivation. So output y equal to G2 times V. Okay, G2 times V. And what is V? G1 times U. G1 times U. So from output to input, the relation is G2 G1. Okay, that thing I have written here, G2 G1, single block. Okay, here there are two blocks are here, I represented with single block. If you talk about CISO system, single input, single output, you write either G2 G1 or G1 G2. Okay, in MIMO system, make sure that it is G2 G1. Next we have parallel connection. So see the mathematical derivation, y equal to G1 times U and G2 times U. Okay, I have taken here G1 plus G2 times input U common. So since the single block representation is G1 plus G2 for parallel connection. For series connection, G2 G1. For parallel connection, G1 plus G2. Now come to feedback connection. Okay, as explained here, feedback connection. So how do we represent a single block? See the mathematical derivation. Observe at this point here. Okay, at this point, this is the one input and this is the one input, right? So U minus or plus G2Y, G2Y. So the point here is G2Y. This is one input and this is one input. So U minus or plus G2Y. To get an output Y, it has to multiply with G1. Okay, G1. So this is your Y. So I clubbed here Y terms together. This is basic algebra. You can do it. Okay, I expanded this bracket and I taken this Y this side, and finally I written Y equal to this expression. Okay, so finally this feedback connection I represented with single block. You can remember in this way. In numerator, we always write the feed forward path gain. Okay, in feed forward path we have G1. That's why here we have written G1. In denominator we start with 1 minus. Okay, 1 minus. Since we have minus here, we have taken plus. Plus it will become minus because your multiplication factor is minus. Then we write here forward path gain. The forward path gain is G1. Then we write here feedback path. Feedback path we have G2. That's why I have written here G2. You can remember in this way also. So these are some basic connections: series connection, parallel connection, feedback connection. Now I'll discuss about manipulations. So I have taken here 4 cases. The first 2 cases related to takeoff point. Okay. So from here we have some signal coming out. We want to take this signal and we want to keep it this here. So what changes we need to do if we want to shift this takeoff point from here to here? So observe here. Okay, let me use different pen. The gain here, right? When you move from input to output, the gain is 1. Okay. So when you shift this takeoff point from here to here, the gain should still remain same 1. That's why I have multiplied here with 1 over G. Because when you move from input to output, the gain G is multiplied here. That's why I have taken here 1 over G. The second case is we have the takeoff point here. Now we want to shift this takeoff point from here to here. So when we shift, what changes we need to do? See here, when you move from input to output, okay, the gain here is the block G. Okay, we have block G here. So when we represent this point here, right? So we need to have still G only. So that's why I have added here block G here. So when we move from input to out, we have the same G. Okay. Now come to summing point. See here, to this summer block, some signal is getting summed up. Okay. And we want to move this summing point to here. Okay. So observe here in the same way. From input to output. Okay. From input to output, we have here G, right? So when we shift the summing point here, still from input to output, we need to have G only. That's why when I shifted the summing point here, I have added here block G. So that from input to output, when we move, the block G is there. Now consider the other case. We want to shift this summing point from here to here. Okay. So what changes we need to do? So see here, when we move from input to output, we have 1. Okay. There is no block here, 1. So when we shift here, still the forward path gain has to be 1 only. So that's, see, when we move from input to output, we have here block G, right? So to have 1 here, I have multiplied here with 1 by G. So that this 2 gets cancelled and overall we have 1. That's why when we shift this summing point from here to here, 1 over G block is added. Okay, so these are some basic things about block diagram detection technique. These are the basic connections and these are the manipulations. And I discuss about linear versus non-linear system. Okay, thanks for listening. Thank you.